quantum mechanics. In particular, I want to look at the notation that we have with matrix notation in quantum mechanics. So we have the notation called Bra-Cat notation, which this is a cat notation. And in particular, cat notation is a column vector. And this cat notation has a limited amount of end states. In this case, down here with this a cat, we have 3 states, 3 possible values, situations, whatever you want to call it. But it's not. That's the physics of the thing. The situation is not important right now. So we have the original cat notation, which is in a column vector. It can also be put in the form of, if you look at here, as a bra, which is in row vector notation, row vector. So essentially, discrete quantum mechanics is really matrices and column vectors. That's what you're doing. And a lot of the abstracts is what's going on in the hood. Is things what I'm showing you now. Now we can take the conjugate of a cat A, and we can get what we got here, a 2, 7i, 1, which when you take the conjugate of a real number, it doesn't change anything, but you take the conjugate of a complex number, it does. Very simple. Now, if we want to multiply bra cat, this is bra A, cat A, B. We do a matrix multiplication with a row multiplied with a column vector, and we get an answer here. Very simple, an answer. Multiply the first element on the row with the first element of the column, and so on and so on. And we multiply just like a matrix, 2 matrices, except these are column and row vectors, and we get a value. This value doesn't have a meaning. It can be complex, but right now we're just thinking about the mathematics behind quantum mechanics. Now also I'm introducing another example with the cat notation with the B that has a complex number here. Instead of you having one number with the complex number, you have two numbers, 1 plus 3i. Same thing applies in the operations. Now I'm not going into all the operations of I'm assuming you know about complex numbers. I'm assuming that you know about linear algebra. Those things, if you don't know anything about those things, this information here is no good to you. But this is more or less, if you're going to be in quantum mechanics, you definitely need linear algebra, calculus to be able to do these things. Okay, so let's just say if we want to multiply the same bra, the same cat with the same number. So we got a bra and we got a cat. We do a multiplying row and a column vector multiplication, and we get 54. Now, in quantum mechanics, it's not exactly like classical mechanics. Classical mechanics gives exact values. Quantum mechanics gives probable values. What probably would happen? What is your probability of somehow? That's what is quantum mechanics. The whole thing's about probabilities. It will not tell you where things are at. It only tells you things that they are at for that moment. That means the next moment you check it is not another situation. Things change. Very dynamic. So this is, in order to calculate probabilities with a matrix notation, Bra-Cat notation, you, just like the continuous version, I'm assuming that you know something about quantum mechanics, is that you need to normalize a wave function, normalize a Bra-Cat or a cat. It needs to be normalized. Is this normalized? This, chances are this is not normalized. The way you find out if it's normalized is if you multiply these two together and you should get 1. Not normalized. This is get 54. So we need normalized. In order to normalize, we got to get the norm. And to calculate the norm, you do a broadcat multiplication and take the square root of it, and you get 3 square root of 6. We do it for B. Let's just do it for B, and we get 9. Get 9. Simply, if we want to get normalized, we normalize by taking the cat, take the cat value, divided by the norm, which the norm here is 3 square root of 6. Norm, this cat column vector is a column vector, like I said. And your norm, you take the 1 over the norm, which is 1 over 3 square root of 6. You multiply you together, you got, and I put a little curve over the top of the A. This is your normalized cat vector. Now, if we multiply the broad of this A vector with this, we should get a 1. Everything should equal 1. It'll be normalized. So check and see if that's true. But this is just a little short introduction to, or under the hood look at what is going on with these little design, these symbols that look like complicated math abstracts, which is not, it's not really that complicated. It's just abstract. You're not seeing what's under the hood. So it makes, if you see what you need to multiply together and see the dynamics of matrix multiplication with column vectors and row vectors, it makes it a little easier to navigate when you're trying to calculate eigenvalues, eigenvectors, and expectation values, and what you're trying to do when you're trying to characterize a system and you're trying to calculate values or measurements of a system. So I hope this helps. This is Alpha Mad Scientist. Like, share, subscribe. I hope this helps. Got more videos coming like this, which is going to talk about a little bit more about doing these type of calculations, which I think it will help. It makes students studying quantum mechanics, and they see these things, it makes things a little bit easier than studying quantum mechanics. Won't be so abstract. But once again, like, share, subscribe. I hope this helps.